Introduction to Power Series. Objectives. By the end of this lesson, you should be able to define a power series centered at x equals a, explain the difference between Taylor series and Taylor polynomials, define the interval of convergence and the radius of convergence, and determine if a power series converges for particular values of x. Okay, so before we look at a formal definition, informally, a power series is a polynomial-like function with infinitely many terms. So let's recall that a Taylor polynomial has a finite number of terms. So in general, a polynomial has a finite number of terms. So the Maclaurin polynomial for sine x was given by, well, sine x was approximately x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial up to some finite n value. So we know that this finite n exponent here was going to end up being an odd number, and this was going to have to end. A Taylor polynomial must end. But what we're going to do now is think about a polynomial-like function that has infinitely many terms. So, in other words, including a plus ... and saying that this series is infinite and goes on forever. So we just finished saying the sine function is approximately the Taylor polynomial given here to the right that definitely ends at some finite term. Well, this image depicts the sine function and different order Taylor polynomials. So n equals 5 means that this red graph is the graph of the 5th order Taylor polynomial. And then n equals 17, n equals 29. And then let's take a look at this 35th order Taylor polynomial for sine x. So you notice that the higher order we go, the better approximation we get for the sine function furthest away from the center 0. So it looks like the 35th order Taylor polynomial is a good approximation all the way up until maybe an x value of 14, and then a negative 14 is going to be a good interval where the sine function is going to match the 35th order Taylor polynomial. So if we increase that order, it stands to reason that we're going to get better and better approximations further and further away from the origin. So what if we just keep going? So it turns out that sine x is exactly, so not approximately, exactly x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on and so forth forever. So if this idea is a little bit hard to understand, it's because talking about the infinite isn't an easy concept. So we are starting to get to some tougher stuff in mathematics, and this idea that the sine function can be represented by this infinite series, so we're adding up a bunch of different things, and that list goes on forever. So this is an infinite series that we're saying is exactly the same thing as the sine function. So we're now going to take a look at how to generalize this idea of an infinite series representing a specific function. And in fact, that infinite series that includes the variable x is what's called a power series. Alright, so before we keep going, I want to stop and talk about the big picture. The main idea is that first we study Taylor polynomials, which only approximate the original function near the center x equals a. And we can keep increasing that order, and we can get a better and better approximation further away from x equals a. But ideally, we would like to use Taylor series, which is a special type of power series that represent functions exactly. So they are the original function, usually. And in the next example, we'll talk about what that part means. So there is going to be a little caveat to having a Taylor series represent a function exactly. Alright, so here's an example that we did take a look at earlier, the Maclaurin polynomial for 1 over 1 minus x. And we recognize this to look like a over 1 minus r. And that's how we arrived at the Maclaurin polynomial of 1 plus x squared all the way up to x to the n. So right now we're still talking about the polynomial, so it is a finite number of terms that we're adding together. And so this black graph right here is the graph of 1 over 1 minus x, and there's actually another portion to that graph over here. So this portion down here and this curve right here are 1 over 1 minus x. So now let's take a look at the different ordered Taylor polynomials. So here's the n equals 1, so the linear approximation, near 0. Again, we're talking about what's going on near 0. And then you'll see this is the fourth order Taylor polynomial, so we can sort of try to follow that curve. So that's pretty good. And then if I increase my order to 10 and 30, so hopefully you can see these different order polynomials here, and how this black curve is the entire function. And even though we got to a order 30 Taylor polynomial, this blue curve here, well, it's only a good approximation, the 30th order Taylor polynomial, for what looks like -1, maybe up until about 1. But it doesn't look like it hugs this curve, 1 over 1 minus x, anywhere to the left of -1. So it wouldn't really matter here if I added infinitely many terms to the end of this, so that 1 over 1 minus x is exactly 1 plus x plus ... This still would only make sense, it looks like, over a particular set of numbers. So even though I've increased my interval or my order to 30, it still doesn't really look like it's going to let me extend past what looks like the smallest x value is -1. So let me just scroll down a little bit. I want you to notice that the Taylor polynomials are good approximations near x equals 0. But they start falling apart outside the interval from -1 to 1. So from -1 to 1, they're all pretty good approximations, better and better as I increase my order. But outside of that interval, -1 to 1, they no longer become useful anymore. The reason for this is that the sum from n equals 1 to infinity of x to the n is a geometric series. And what do we know about geometric series? That they only converge for x values less than 1. So another way to write this, or the absolute value of x less than 1, is when x is between -1 and 1. Which, if we go back and look at the graph, from -1 to 1 is really where the nth order Taylor polynomials are accurate, are really good approximations. And outside that interval, they fall apart. So now let's try to look at the formal definition of a power series and then see where we can go from there. Alright, so here's the formal definition. A power series centered at x equals a is an infinite series of the form n equals 0 to infinity of c sub n times x minus a to the n. So let's just actually expand this a little bit. So we're starting with an index of 0, and remember 0 gets replaced anywhere there's the variable n. So this would be c sub 0 x minus a to the 0 plus c sub 1, and then x minus a to the 1 plus c sub 2 x minus a squared, and so on and so forth. So this would be the expanded version of a power series. And this c sub 0 is almost its own series. So if you kind of think about, if I removed this x minus a to the n portion, the sum of n equals 0 to infinity of c sub n, well, that would just be an infinite series of itself. So the coefficients that are in front of the x minus a to the n term are themselves in the form of an infinite series. So the only difference is that when we add the x minus a to the n term, the x doesn't go away. So I'm not substituting in this n for x, the x is going to stay there. Because remember, I want this to look polynomial-like. And the fact that we chose n equals 0 is arbitrary. The index can start at any positive integer we want. Alright, so before we keep going, let's take a look at some concrete examples. So a power series is an infinite series, but it's also a function of x. So we're going to need that variable x to stay in once expanded. So here we have the sum of n equals 1 to infinity of n squared. So that this portion here is in place of my c sub n. And then this portion is the x minus a to the n part. So if we start substituting in the n values starting at 1, I'm going to get 1 squared, well that's 1, times x minus 3 to the 1, plus 4 times x minus 3 squared, plus 9 times x minus 3 cubed, and so on and so forth. And then here's a second example. Well, that c sub n doesn't technically need to have n's in it. So in other words, I can have this be a constant function. So right now, c sub n is a function of n. In this second example, c sub n is the boring constant function too. So now the nice thing is we really are only plugging in the index into the exponent of the quantity involving x. So x plus 2 is the only thing that involves the n as the exponent. So 2 times x plus 2 quantity to the 1 plus 2 times x plus 2 quantity squared, and so on and so forth. So it's possible for that c sub n to be a function of n, or it can just be a constant. Alright, so here's what we're interested in finding. We want to find the set of all values of x for which the power series converges. This is also known as the interval of convergence for the power series. So let's take a look at that previous example that I left up here. We just talked about that, where the constant, or the c sub n was a constant function, just 2. So what I'm looking for is what are all the different x values I can plug in right there that will make my original series converge. So let's think about actually plugging in numbers, because these are all real numbers that we're attempting to plug in. So what I'm going to do is I'm going to go ahead and try to evaluate this series by letting x equal 1. So now I have this 2 in front, that's not affected, and what I'm about to do is let 1 be substituted into x. So I have 1 plus 2 quantity to the n. Well, I can simplify this. This is the sum of n equals 1 to infinity, and then 2 times 3 to the n. So what I want to know is whether or not this series converges. Because if it does, then x equals 1 is in the interval of convergence. So it's a part of a set of all x values that's going to allow the original series to converge. Hopefully you recognize this to be a geometric series. This looks like a r to the n. And the only way that this can converge is if this value, this r value here, the absolute value is less than 1. And 3 is not less than 1. So this series does not converge at x equals 1. Or it diverges, which means that x equals 1 is not in the interval of convergence for this power series. So our goal is going to be to find, well, what x values do make this thing work? What x values are going to allow the original series to converge? And what that's going to tell us is it's going to help us figure out where this power series actually matches the graph of that original function. So that's kind of the goal, is what we're trying to find, is where is this a good approximation for the original function. It's important to know all power series converge at their center, x equals a. So in this case, this series is centered at -2. So if I were to substitute -2 into this power series, because remember the general formula is c sub n x minus a, so my a value is -2. If I were to substitute in 0, or -2, that would make this inside part 0. 2 times 0 is 0, so I can add up 0 infinitely many times and get out 0. So the power series is always going to converge at its center. And the next definition is the distance from the center to either endpoint of the interval of convergence is called the radius of convergence, and it's denoted with a capital R. So in other words, right now, the example that we can use is when I had that function 1 over 1 minus x. Whoops, didn't look like that. It looks something like this. And we said that between -1 and 1, I had some pretty good Taylor polynomial approximations. But outside -1 to 1, that wasn't a very good approximation. So the radius of convergence is 1, because that's the furthest distance from the center 0. So let me try to get a different color. So from the center 0, the distance from the origin to the end of the interval of convergence is my radius of convergence. So in this case, r equals 1. Now, I want to be really careful here. I'm not entirely sure, based on that picture, what the exact interval of convergence was, just based off the picture alone. So we were able to decide, because that series was geometric, that the interval of convergence really was -1 to 1. So that's how we knew that for sure. But based off the picture, we couldn't really tell if we include the endpoints or we don't include the endpoints. And that's really the focus of the remaining couple of sections, is to find the interval of convergence, and then we're going to have to test the endpoints. Okay, so we're kind of going to stop our discussion on the interval of convergence because, as I mentioned, that's pretty difficult to find an interval of convergence, and we're going to have to test the endpoints, and it's going to be a process that takes the next couple of lessons to get through. But we are going to focus on the radius of convergence, which is easier to find. And there are three possibilities for the radius of convergence. The first possibility is that the radius of convergence is 0. And this is a really bad case. So this is where the power series only converges at its center. So only converges at that A value. Now, on the opposite hand, the best case scenario is when the radius of convergence is infinity. So this is kind of ugly notation because this kind of indicates, or it looks like maybe that R is a number. But what this really means is that the radius of convergence is infinite. So the series converges for all x values. So the example that I can tell you here is when we have f of x equals sine x, which we said was exactly x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus etc. So sine x was exactly this Taylor series, this special power series, and it looked like the higher we went in order, the better approximation it was for sine, the further and further we got from 0. So further and further away from that center value 0. So in fact, this is exactly sine x over all real numbers, from -infinity to infinity. So that's the best possible scenario. And the third possibility is that R is some positive finite number. So in that example of the 1 over 1 minus x, it looked like there that our radius of convergence was 1, because our interval of convergence was -1 to 1. Now, in this case, the series converges when the absolute value of x minus a is less than r, and diverges when the absolute value of x minus a is greater than r. And to determine what happens when x minus a equals r, we must test what happens at the endpoint. So this is that whole finding the complete interval of convergence, and most of the rest of this chapter is a collection of tests needed to test the convergence or divergence of infinite series. So that's the portion of this section that's going to take a little bit of time to develop all of those different tests so that we can finally get a conclusive interval of convergence. So for now, we focus on this radius of convergence. All right, let's look at an example. So I have the power series given by the sum of n equals 0 to infinity of c sub n times x to the n. And we know that this power series converges when x equals 3, but diverges when x equals -5. For each of the following x values, state whether the series converges, diverges, or cannot be determined. Okay, so this power series, I'm going to rewrite it right here. So n equals 0 to infinity of c sub n, and x to the n tells us a lot. It tells us that my center is 0, because the general form of a power series is c sub n times x minus a to the n. So this is a really generic way of writing a power series. And what I want to do is I want to think about a graph. So I don't know what the function at all looks like, but I know that my power series is going to be centered at 0. And what I know for sure is that at the x value 3, so let's say 1, 2, 3, I know that my series has to converge. So I'm going to put a little c above the number 3. And then I know that at x equals -5, my power series diverges. So 1, 2, 3, 4, 5 in the negative direction. So this is all I know right now. So let's talk about possibilities here. So I know that my series converges all the way up until this x value of +3. So here's one possibility, is that my interval of convergence can be from -3 to 3, and I could include 3. So I'm going to go, possibility 1. my interval of convergence could be from -3 to 3. And I could not include 3, but -3, but I have to include +3 because I was told that my series converges at 3. So, in other words, the smallest radius of convergence I can possibly have with the two pieces of information I was given is a radius of convergence of 3. But testing the endpoints is another story. I don't have any pieces of information about the actual power series itself. So this is one possibility. This is the smallest interval of convergence I can possibly have. So possibility number 2 for the interval of convergence is I know that the series diverges at -5. So if the series diverges at -5, I know that at -5 I have to have an open set of parentheses, but it's still possible for the series to converge over here at +5. So I could also have this be a possibility for the interval of convergence. But if I go anywhere to the left of -5, I definitely have to diverge. And if I go anywhere to the right of +5, I definitely have to diverge. So my interval of convergence is centered around the center. So the smallest can be from -3 to 3. The biggest can be from -5 to 3, but we have to keep, or -5 to 5, but I have to keep in mind the possibilities for the endpoints. So what the rest of the question is asking me to do is for each of the following x values, state whether the series converges, diverges, or it cannot be determined from the information given. So at -6, so if I put -6 on this number line, if my power series diverges at -5, that must mean my power series diverges at -6, because now this is outside of the potential biggest interval of convergence. So this was the smallest possibility, and this was the biggest possibility for my interval of convergence. So anything outside of that is definitely going to have to diverge. So -6, this diverges. Whoops. Alright, -4. So -4 is right here. And what I know is that the smallest interval of convergence is from -3 to 3. So within this interval, every value in this interval has to converge. But -3, I don't know what happens there. And really, I don't know what happens at -4 either. So that's arbitrary. So at -4, there's not enough info to determine whether the series converges or diverges at -4. So this was the smallest possible interval. This was the biggest possible interval. But -4 falls in between that. So I don't really know what happens there. At -3, well, because I don't know what happens at the endpoints, at -3, we said the smallest interval was an open parentheses around -3, meaning we don't include it. So once again, there's not enough info. So I'm going to put cannot be determined, as that was one of the options in the question. Now, -2. The smallest possible interval of convergence is from -3 to 3, including 3, but not including -3. Well, -2 is in that smallest possible interval. So that must mean that at -2, I converge. So similarly, at 0, 0 is in the smallest possible interval of convergence. I'm also going to converge. And at 2, still in the smallest possible interval, I also converge. So now let's think about what's going on at 4. So I know I have to converge between -3 to 3. That's the smallest option. The biggest option was from -5 up to 5. But 4 falls in that gray space where I don't really know what's going on there. So at 4, it's possible for my series to diverge. So really, not enough information. I don't know whether it converges. I don't know whether it diverges, so cannot be determined. And then finally, an x value of 6. So anything to the right of 5, we said has to diverge. Because if the series diverged for -5, well, then that means the biggest possible interval of convergence was from -5 to 5, including 5, and 6 is outside that interval. So this thing has to diverge. So these are all the different possibilities for all of these respective x values, just given one x value where I converge and one x value where I diverge. Alright, I think these are pretty tricky problems, so let's try another one. So this time we have this generic power series, and our center this time is 2. So I'm just going to draw a horizontal line, and I'm going to go ahead and put 2 right in the center. So just to be clear, I know that my power series has to converge at 2 because every power series converges at its center. So out at 2, I'm going to go ahead and put C, but I'm going to make it a thicker looking C so I also recognize it as the center. Alright, now I know that my power series converges at x equals 3. So right here at x equals 3, I know my power series converges. So my smallest interval of convergence, so right now what that just told me is the smallest possibility for the radius of convergence is 1. So, whoops, not negative. So right here, this x value is 1, and at 1, it's possible to converge, but it might diverge. I'm not sure. So if my radius of convergence is 1, this is the smallest possibility for the radius of convergence. Oops. So then that means that 1 in the other direction gets me to the other side of the interval, but to test the endpoints again in the interval is something that would require me to have the original power series, and we haven't done that yet. So right now, the smallest possible interval of convergence is going to be from 1 to 3, where I know I converge at 3, but I'm not sure what happens at 1. So I might not include 1, so that's why I'm not going to include it, and that's what's going to make it the smallest interval of convergence. So now I know this thing diverges when x equals -5. So let's do that one in a different color. So 0, 1, -1, -2, -3, -4, -5. So I'll extend the number line over here. So I know over here at -5 that my power series diverges. So that's with the biggest possible radius of convergence. So our center was 2. So the distance here from -5 to 2 is a total of 7 units. So my biggest possible R value is 7. So this is the biggest possibility for the radius of convergence. And so I could potentially go 7 units in the other direction as well. So I'll just extend this out. That would mean that 9 is the other side, the other endpoint, 7 units away from 2 on the right-hand side. So my biggest possible interval of convergence would be from -5, and I know that I don't include -5, all the way up to 9. And I know that I don't know what happens at 9. I could converge, I could diverge, but I want to know the biggest possible interval of convergence. So I could converge at 9, so I'm going to go ahead and include 9 because that's a possibility. That's the biggest possible interval of convergence. Alright, so now let's think about what's happening at every single one of these points. So, -8. Well, that's way over here, right? -8 is to the left of -5. So the biggest possible interval of convergence was from -5 to 9. -8 is not in that interval, so I definitely have to diverge there. So I'm just going to put a little d. Alright, now -6. -6 is also to the left of -5, so not super interesting, also diverges. -2. So -2 is right here. And we said the smallest possible interval of convergence was from 1 to 3. So everything inside this interval I would have to converge. And anything to the left of -5 or to the right of 9 I'd have to diverge. But -2 is in this gray area where I'm not sure. So the answer here is cannot be determined. I don't know. Same thing with -1. I don't know exactly what's happening at -1. It falls in that gray area. So this too cannot be determined. And similarly, 0 falls in that interval, so cannot be determined. And well, 2 is the center, and every power series converges at its center, so we can declare that at 2 the power series converges. And so now let's think about 5. So at an x value of 5, say right about there. Well, everything in this interval from 1 to 3 definitely has to converge. But the biggest interval of convergence was from -5 to 9. So 5 is not outside of 9, and it's in that gray area again where I'm not sure. So 5 is also cannot be determined. 7 falls in that same gray area that cannot be determined. And 9. So at 9, I'm not exactly sure what happens. The biggest possible interval of convergence was from -5 to 9. And I conclusively knew that at -5 I diverged. But at 9, that's the other endpoint with the radius of 7 away from 2. This may or may not converge. We're not sure. It's the biggest possible x value where I might converge, but at this point, we don't know. So the last one is also cannot be determined. Whoops. Cannot be determined. So this was actually kind of a boring set because a lot of them we couldn't really tell. The only ones that we can tell are between 1 and 3. So let's go ahead and add a problem here. Let's go ahead and add, let's say, 1.5. So at 1.5, just to make clear that we're not just talking about whole numbers here or integers, if at 1.5, that does fall in the smallest interval of convergence. Everything in this interval has to converge. So 1.5 falls in there, so I could conclude that at 1.5 the power series converges. So this is definitely something that comes with practice, and it takes a lot of thinking about and understanding the difference between the radius of convergence and then understanding that we can't tell what happens at the end points of our intervals of convergence, our smallest and biggest possibilities for endpoints of convergence.